constants. So please, Volodya, take over.
So to add in n equals 4 super Young-Mills theory. Mm-hmm. Good. So the title of my talk, first of all, thanks a lot for the organizers to organize this very nice conference, and congratulations to everybody who was present on the previous conferences. It's our 20th anniversary of this conference. The first one, I'm proud to say, was organized 20 years ago in École Normale Supérieure in Paris. So long life to integrability and engagement in string theory. So the title of my talk is the longest on this conference, so it can serve already as a little introduction. Let me add something to it. So in fact, let's speak first about hierarchy of operators in n equals 4 super Young-Mills at n going to infinity, at large n. So we can distinguish small operators, like with dimensions proportional to 1 in the large n limit, which I kept equal to 1. Then we have, of course, strings on ADS as a gravity dual. Then we have integrability for the spectrum of such operators, etc. Then big operators, when the dimension is of the order n. So it's still ADS. Of course, there are heavy objects in ADS. So integrability, I leave it to the comments of those who worked on it on giant gravitons, for example. And apparently there is some integrability left here. And finally, we have huge operators. Huge operators with dimension of the order n square. Then obviously these operators already perturb strongly the vacuum of the theory, and they intervene with the action in the larger limit. You have to say, if you work in some saddle point approximations, you have to take into account not only the action in this saddle point, but the operator itself. And already you have deformed ADS space. We suspect that black holes are only possible in this regime. Of course, it's very difficult to analyze such states. And we have probably no integrability. No integrability, although who knows. But we have a particular nice case in this theory, namely the 1/2 BPS operators. And here we can do something. First of all, gravity dual is this famous Lin-Lunin-Maldacena background. Then structure constants and dimensions and dimensions protected by supersymmetry. And now it's, first of all, now it's really the subject of my talk. For general huge operators, we have a matrix model. Is it visible? I don't know. Then this matrix model is solvable by by Hopf. I should really first write, where is the name of Riemann-Hopf, as I was taught by Paul Wigman, who explained me the history of the subject. Fluid dynamics. And then I will give some particular examples. Maybe explicitly, some of them are explicitly solvable, and these last 3 points are the subject of our recent paper with Pedro and Harish present here. So in this recent paper, which appeared, I guess, a week ago or 2 weeks ago, I forgot. Okay, and I see.
Right.
Yeah. Now better. And so let's study these 1/2 BPS huge operators. First of all, just in general, 1/2 BPS operators. And apparently the orthogonal system of such operators, that's what we need, can be given by a character in representation R of a field which is simply this scalar field. We have 6 scalar fields, and we project them to the vectors y, which is like. And it's well known that, of course, this combination is protected, 1/2 BPS operators, and any function, invariant function of them, is, of course, protected. And the representation is characterized by some Young tableaus. So it's GLN representation with n columns. So it's 1, 2, etc. n. And we have highest weight components, which we label like lambda 1, lambda 2, the length of the rows of this Young tableau, and the character is given of any such field, phi, say, is given in terms of eigenvalues as the Weil formula. It's a determinant of phi j to the power h k over j k from 1 to n, divided by van der Monde determinant of phi's. You remember what is van der Monde determinant? It's just product of phi I minus phi j. And hk are defined through lambdas in a very simple way. This is a very useful shift of all these weights, so we call them shifted highest weights sometimes. It's just this formula. So the weights are just ordered and the highest weights are strictly ordered, which is convenient. So you immediately write the formulas in very compact way. Okay, so if you have particular representations like that, for example, chi of this representation will be given, as you know, 1/2 trace phi squared minus trace phi squared. And you see that in principle they are sure polynomials. Any such character for any representation is a sure polynomial of traces of powers of phi as arguments. And then if we compute the correlation function of such operators, better x1, x2, it's very easy calculation done by many in many ways. It will be n factorial product of hj factorial 2 to the power hk from 0 to n minus 1 plus k minus 1 over k minus 1 factorial. So it's then they appear to be, as I promised, orthogonal with respect to this representation characterized by h's. Yes, when I write R, I mean the collection of these lambdas or h's. And then the trivial kinematic factor, it's a product of y times y prime. It's R prime here, over x minus, I should keep the same notation, x minus x prime squared to the power of to the power L LR, where LR is simply the number of boxes, the number of these entries of field phi. And this is actually twice. And LR, the size of the Young tableau, serves also as a it measures the dimension of this operator, which is protected. Yeah, and now for three such operators, so you understand that those are three Young tableaus. We have some coefficient, which I call Z3 of these three representations, depending on these three representations, and then the product of yi dot yj to x I j square, and all that in the power Lij. I and j run from 1 to 3. I mean, all these combinations which you find in the conformal three-point correlation function of Polyakov. And Lij are so-called bridges. Li plus Lj minus L1 minus L2 plus L2 minus L3. So this is a very standard expression, nothing special, but this number, is precisely the structure constant, which we are after, which we want to compute. And since it's a protected quantity, it's known to be protected for these operators, the answer for it will be purely combinatorial. Namely, essentially you, and even for any n, you have to say, to define these operators. And pictorially, I have the traces, say trace phi cube, phi squared, trace phi 4 here, and this is, say, the same operator in the same operator. Then I have maybe some operator here, trace phi square, some operator there, phi square. So it's 3 possible operators. You see that you can have products of such traces, of course, in the operator. Just pictorially, it's one of the terms, and what we do, we just connect them by propagators. So all these powers come from just propagators of free fields in the theory, scalar propagators. So we start connecting them like that, for example, double line propagators as usual. I don't know, this way, so I don't continue. You cannot connect. I mean, here, of course, I didn't draw enough of these guys. Okay. Anyway, you connect all of them in all possible ways, and you get some number, the number of possible connections between them with propagators. And in the large unlimited, it's not really a planar object because the operators are huge. Why they are huge? Because we will take in the large unlimited all these dimensions of the order n, such that the volume of the Young tableau, the number of boxes, is of the order n square, of course, if you sum up all of them. So we take this big Young tableau, and now let's try to invent some matrix model which computes exactly this combinatorial quantity, the number of connections between these Schur polynomials of traces of phi's in some power, in various powers. And the matrix model can be presented in the following way. So this Z3 is integral of product of 3 matrices of the size, of course, of n color, n number of colors. It's from, so there are 3 integrals. Then we have the following measure, n over 2 trace sum of mi squares, again from 1 to 3, minus twice sum I more than j, mi mj, all this under square, and then we write the product of characters, product of 3 characters, ri, as functions of m. So I claim that this model solves the problem of counting of these kind of propagators, and that's why it's equal to the structure constant. Why it's so, okay, I have no time to really explain it in detail, but you can try it as even just not as a matrix, but for n equals 1, just 3 integrals, and you will see that it solves this combinatorial problem of all these connections. It's designed so that the matrix Mi and say Mi and Mj, they somehow connect ith and jth operator, and there are no self-connections. So it's just the coefficients in the section are so that there are no self-connections. So it's precisely what we need. So this is the first message, and then this is a difficult model because you have these angles, SUN angles between the three matrices. It's difficult, of course, to do whatever with it. You cannot. Usually, you solve matrix models when you reduce them to eigenvalues, but it's very difficult to reduce them to eigenvalues of M directly. But indirectly, you can do it because there is a trick which I invented long ago for solving the Potts model on planar graphs. And you simply decouple these matrices by an extra integration, by an extra integration over X matrix with Gaussian measure. And then you have product of these three matrices, e to the minus n m square minus x m. And then you have the character of the matrix MM, MA, with representation A. So if you integrate over X, of course, this here you have sum over, because you have product, you have sum over MA, M1 plus M2 plus M3. So you get as a result trace of this sum of three matrices, and of course it contains this these cross products with some Gaussian term which fits well to give exactly the same Z3. So this is the first step, and now already you see that the model is solvable, because here we can integrate over angles between X and each of these three matrices. You have three independent angular variables, and you can express this integral only as integral over eigenvalues. Namely, I will write just the result, integral product sorry, I will write the result for first of all, I have to write here, these are three integrals, and I will write the result for each of these integrals. Now they are decoupled. They all depend on X, but for each matrix M, these are independent integrals. And you can represent them through eigenvalues of M. So M1, Mn are eigenvalues of matrix M, and we have the following. Okay, Mi square, Vandermonde square of Mi, of M, and then we have, now we can perform the angular integration between X and M using so-called Harish-Chandra Isaacson-Joubert formula, and we get determinant e to the Mi x xj ij over Vandermonde of X Vandermonde of M, and what is also remarkable, so we are computing each of these integrals, yes, because then we can also integrate over eigenvalues of X, and the character is also expressed through a similar Isaacson-Joubert kind expression, which is determinant of mk to the power hl, the Weil formula, Vandermonde of M. Okay, so now we can, of course, write here also the measure, transform it. Nothing depends on angular part of x, so you'll have product dxi's e to the minus xi square, Vandermonde square of x, and the whole thing becomes just eigenvalue integral, which is subject to saddle point computation, and which is in principle calculable. Moreover, this integral can be taken explicitly. Each m, if you just expand in n factorial terms, sum of n factorial terms, each determinant, you will notice that you can independently integrate over each eigenvalue m, and you get the following nice results. It's e to the minus sum xi squared over 2, I guess. I drop the factors of n everywhere. Just, you can always scale it there and back. And times q, which depends on the representation r, on the representation of the character, of all these eigenvalues, x1, etc., xn, where this guy, qr, is a nice object. It's a Slater determinant, essentially, up to some exponents. I could even absorb exponents there, but it's determinant of Hermite polynomials hk of xl, for example, divided by Vandermonde of x. So essentially, it's Slater determinant, the wave function of free fermions in the quadratic potential, with energy levels, field energy levels, which correspond to these shifted Hyatt waves hk. They serve like energy levels in this Slater determinant, and so the problem reduces to the computation of this also quite a complicated object, the Slater determinant. So there are some cases which we can treat explicitly, because, for example, if we take the case of, say, suppose, maybe I have to start to erase something. Suppose we fill only even levels in this Slater determinant. This is already not empty quantity. If we fill all the first levels, of course, just it will be Vandermonde of x over Vandermonde of x. It becomes just 1. The unity operator, qr, becomes 1. But if we fill every even level, like imagine you have this quadratic potential, you have levels, but you fill every other level, like the first, the third, the fifth, etc., corresponding to even only even energy levels, even wave functions. Then q of x, x1, etc., xn, of such object, how to denote it? I denote it in the following way. In principle, it corresponds to the Young tableau, which is filled in this way. So you jump always like always by 2 here, decrease by 2 the highest weights. So it looks like a triangle, Young tableau. Then it is Vandermonde of x square over Vandermonde of x, and which is product of xi minus plus xj squared. No, xi plus xj, I more than j. If you plug in this in our integral over x, you will realize that z3 for this triangle, Young tableau, is given as integral product dxi e to the minus xi squared, and then you have van der Monde square of x, and you have this product of xi plus xj, I more than j, to the power cube, which appears to be, Charlotte should recognize it immediately, appears to be O minus 3 ON model of on random graph of Ivan Kostov, 98, something like that. And for n equals minus 3, which is a solvable case, of course. And solution is given in terms of elliptic functions, for example, for the density of x's, for a row of x, of course, at large and limit. At large and limit, it is an elliptic solution, explicit solution, given once in the paper of Einar Charlotte Christiansen. So we used it, and we sort of brought it to a sort of nicer form. And from there, you can calculate explicitly Z3 for three triangular Young tableaus of big size. Yes. So it's e to the minus to the n square times 0.4465. One can calculate many digits here. So I think, to my knowledge, it's the only. It's 10 minutes because we started slightly later. To my knowledge, it's the first structure constant of three huge operators, which is explicitly computed. I don't know any other example, but of course we can be more ambitious here with our representations in terms of eigenvalues and try to compute something more. To describe this solution in general, and to attempt some computations for particular more complicated Young tableaus. Namely, for example, we worked out nice integral equations for rectangular Young tableau, which is the size of nk. So in the large and limit, it also reduces to some nice integral equations for x's, but we don't know how to solve them yet. They should certainly be solvable, but one should work out some algebraic curves for them. Then also so-called trapezium case, which is the generalization of triangle case. So we have the Young tableau of this size, of this kind of shape, and you have k, and here you have this triangle, like this kind of feeling. And there exists, it's possible to do something with these cases to reduce to such integrals, because there are beautiful formulas which I discovered in Edward Mazeng's paper, but probably I don't know whom they belong to. You still don't tell me, but I should write this formula. So Q for rectangular case, for example, rectangular case with this k size is given in terms of this nice matrix integral. Maybe Brezan-Hikami, for example. I'm not sure it's exactly the formula they have, but they worked with this kind of representations. M square, product of determinants of x alpha minus m alpha from 1 to n. You see, it's k by k integral, not n by n, but k by k integral. But we have big sizes, of course. N and k are, k is of the order n, to make it interesting. And of course, you easily diagonalize it for eigenvalues of m, and one can plug it into our Z3 and find also the representation of similar kind. At least in the large and limit, it reduces to some singular integral equation of the same kind as for an ON model. Okay, and similar representation exists also for trapezia when you just have only even polynomials, but they also represent orthogonal system of the system of orthogonal polynomials, so one can generalize this formula, which we have done in our paper. Okay, and now five minutes, yes. Now, how to solve it, a few words how to solve it in general. How to reduce it to the Riemann-Hopf fluid dynamics. Namely, the Isaacson-Joubert integral, Harish-Chandra integral, was analyzed in the papers of Matitz and Dazjevitsky, and it was recognized, especially in a nice paper of Matitz. Long ago, it was recognized that it can be reduced, the calculation of Isaacson-Joubert can be reduced to fluid dynamics. Namely, this is the following integral. So let's write it as H, A and B. A and B are two systems of eigenvalues. So it's integral over SVN Haar measure d omega e to the trace omega dagger A omega B, yes, where omega are it's the SUN matrix, and A and B are diagonal matrices of eigenvalues. And then the result is up to some normalization determinant e to the AI bj over Vandermonde of A, Vandermonde of B. And it was noticed in this in the papers I mentioned that log of such integral in the Largen limit can be reduced to the computation of this log can be reduced to the following, the computation of the following action. Suppose you have here I label T and T prime, these eigenvalues, and I generalize sort of this. I say that not only you have row A and row B, but I say that there exists the intermediate row of X at the time T. So I introduce a new parameter, the time, such that row 0 of X of A is row A, and row 1 of here it's of B is a row of B. By A, B, and then X I mean again the eigenvalues, but we can work with densities and the Largen limit. So we have this action dt integral dx rho t of x, and here we have v square, the velocity, which we will associate with some velocity of the fluid xt, plus p square over 3 rho cube of tx, plus some uninteresting boundary terms, which depend entirely on the endpoints. And actually, this action is a nice thing, which it encodes the Euler equation with the following equation of states for the pressure which is proportional to rho cube. Then you have second equation, which is Euler equation with this pressure in the right hand side, and these two equations can be encoded into one simple Riemann-Hopf equation for the function xt, which is v of xt plus I pi rho t of x, and it's simply this famous Riemann-Hopf equation, f dot plus f prime x equals 0. You can check that if you if you plug in this complex function, you get the system of two equations for imaginary and real part. And then, so we have to compute essentially we have this fluid of free fermions, if you want, x1, x2, etc., xn, which is, of course, forms a continuous density. It develops in time, and we have to compute the whole process in time in order to find the function of initial and final states to compute this integral. So you can characterize it by rho of 0 of x, and you have to arrive at the time 1 to rho 1 of x. So this is one possible. This is the equation of the second order, because you have two equations encoded here. So you can, for example, fix rho at the endpoints, which are this rho A, rho B, the densities of A and B, or you can use the velocity fxt, which is dx delta s delta rho t of x. That's another quantity you can use. So in principle, you can use v x0, or here you can use v x1. So you have to take a pair of these functions, say rho and v, which is initial boundary problem, or v and v, for example. But two out of them should be fixed in order to compute this functional. And then look at here, and it's my last comment. You have this quantity here, which is this Vandermonde h of rho of m, rho of x, and rho of m. Yeah. Then you have character, which is also the Higgs-Exxon-Joubert determinant of actually log of minus log m and h, which I have to write it in terms of rows and some densities. And say I can say that this is rho at time 0, this is rho at time 1, this is rho tilde after going here rho 1, and this is, say, rho tilde at the time t2. So we can see this calculation as a process of computing this, it's Exxon-Joubert determinant, then jumping here with some gluing conditions which are defined by saddle point, and then finally we'll arrive at the density of h's, which we fix. Actually, we have to fix. But maybe we have to use the velocities, not the densities. I have no time to make it precise. And then after you compute these functionals using this equation, and you plug it into the integral of x, you have the and you find the eigenvalue problem for x's already, which is essentially the following problem. It's the last equation I write, dz rho of z x minus z equal to 2x plus sum of velocities so you can view this integral as x node in the middle, 3 integrals like M1, M2, M3. Somewhere in the middle you have to glue together these two Itzhak-Joubert fluids. And then you have to plug in the result of so the fluid goes from here to there. You compute the velocity here out of 3 points, and then the final saddle point equation is of this kind, which is simply the minimization of x integral. And that's actually the general description of computation of this structure constant. Then we, of course, worked out some numerics based on of solution of this equation based on the discrete integrable analog of this fluid dynamics, which is Calogero-Sutherland model, very beautiful regularization, and Harish Murali in his talk, in 10 minutes talk, maybe will explain some numerical results which we obtained using this representation. I think that's it.
So let's thank Volodya for his talk. And before the coffee break, we have time for a few quick questions.
Thanks, Volodya, for a nice talk. So the only thing I want to clarify is, so it looks this hydrodynamic picture like describes more like open strings, right? So
it describes
like open string because you have like a stream. It's like eigenvalues. They have lower and upper bounds, right? And
oh,
so
I don't see this analogy with strings. Of course, here you
because they merge
assume that you have finite distribution. Yes, that's what you mean.
Yes,
but
can I think about it as some string profile? Very
I
roughly.
don't see any immediate analogy. Maybe you see.
Okay.
Of course, it's even
Still open string then.
Yeah, hard to say. Say, of course, m's are eigenvalues of the matrices here, so they are related to operators, original operators. But say, if you see how the analogy between eigenvalues of these operators and strings, I'm ready to discuss it.
Are there ways of generalizing this fluid and adding extra terms to the fluid action? Are there identities that generalize this fluid and that add extra powers of rho or modify the equation of state? Is this the only identity that's known between a matrix determinant and a fluid, or can we generalize this identity?
I don't know any other, because this is a nice object. It's not easy to generalize it, the Itzhak-Joubert Harish-Chandra integral. So maybe some no, actually, one of such generalizations, when we compute the Slater determinant, which is the convolution of these two determinants. This is our method, yes? We, instead of working on Slater determinant, we split them. But the Slater determinant certainly satisfies, I had no time to explain, nice inversion relations. The inversion relations should be also related. I mean, Slater determinant should be also related to some fluid dynamics. Here we can probably describe it, evolve this liquid, this fluid in 2 steps, as I say, using 2 Itzhak-Jouberts. But for example, we can imagine, we know similar formulas for other orthogonal polynomials. Say if your free fermions are in some other potentials, then you have determinants, Slater determinants of other orthogonal polynomials, and who knows, maybe for that object we could also build some fluid dynamics, which I don't know how, but it's quite plausible.
Charlotte?
Okay, could there be any simplifications if you consider 2 huge and 1 large operator?
I don't hear well.
Are there any simplifications if you consider two huge and one large operator?
Very good question. Of course, we are working on it. For example, very natural thing is to compute huge giant graviton correlator, which we are after with my student Prokopy and Podistov, and some other people are involved in the discussion, including the authors of this paper. This is, of course, you can advance a little bit, you can compute some of these integrals, but you end up also with complicated determinant of Slater type, even slightly more complicated, and Bayesian determinant. So, I mean, I'm sure one can advance a lot in many directions, including this one, which is one of very interesting. And of course, it is in analogy of recent work which you have done with Kostya, and then Shota with co-authors, etc. It would be interesting to discuss this aspect.
Okay, one last quick question.
This Itzekson-Zuber integrals, if I remember correctly, are computed by localization. Would it be instructive to do it directly, apply directly in Young-Mills, or will it be the same? Directly start with localization.
Also good point. Of course, this idea comes across anyone's mind when we work with 1/2 BPS. So these objects, maybe there is a possibility of considering these objects using localization, because it's 1/2 BPS and protected quantities. On the other hand, yeah, what can you get by it? Maybe you will reproduce, hopefully you will reproduce just this matrix model, which we obtained combinatorially. One interesting thing, which I, of course, forgot to say, I will mention that it's very interesting to relate it to MML, to LLM gravity background, to Lin-Lunin-Maldacen gravity background. And for example, can we reproduce the result for our triangle structure constant, using LLM, or at least a giant graviton, huge, which is a good starting point, because at least we don't spoil this LLM geometry completely. But otherwise, the problem is very complicated. You have only asymptotically near the operators, you have LLM metric, but then you have to sew it together in somewhere inside this 10-dimensional gravity.
Okay. So we will continue the discussion during the coffee break. Let's thank Vladimir Kazakov again, and